It's a pleasure to welcome Fabio Nobile.
Thank you, David. Pleasure to be here. Okay, so this is actually a small project that we're about to finish. So the paper is not yet submitted. So it started as a master project of Nathan Schaffer. Then my PhD student Matteo Raviola was also involved, and then we developed a little bit more the theory. So now we should be ready to submit the paper. This talk is about stochastic optimization, and which I will introduce very briefly. Actually, we look at some stochastic gradient type algorithm to solve stochastic optimization problems. So reference is I don't know if you know or are familiar with the SAGA algorithm. But in stochastic optimization, often we have continuous random variables. So one of the questions was, can we do sort of SAGA type algorithm, but with continuous random variables? So we came up with this sort of generalization of these control variate techniques based on continuous random variables that try to fit a model over the iteration using the history of the stochastic gradient to improve progressively the convergence until you reach the optimum. So in particular, we have looked at regression type models, so least squares type models done over the history of the iterations, and we look at a little bit of the convergence until at the moment only very nicest case of strongly convex functionals, so where we can do nice theory. Okay, so that's the plan. So stochastic optimization, we want to minimize expected value of some function. So u is the design parameter and y is some random variables that are there. The minimizer is in some Hilbert space, could be finite or infinite dimensional. And y, as I said, I will focus on the case where y is a continuous random variable with a given probability density function rho. And I assume that this function g is smooth. So it's a relatively nice optimization problem, but the difficulty comes on the expectation here that we have to compute or approximate somehow at every iteration of the gradient method. I look in particular to problems where every evaluation of g or the gradient of g is very expensive. So what I'm thinking at really are big computational models like PD type models where you want to optimize or design the system, so optimize some parameters, maybe a shape of an airfoil or some other quantities. But you want to do some sort of robust optimization. So you have uncertainty in the system. So you want to minimize not just in a single scenario, but in a collection of scenarios, having put some probability distribution of the uncertain parameters y. So that's really the focus of this talk. Now I realize that slides are slightly cut. Sorry. It's a usual problem. Okay, let's see how much is cut. Otherwise, I will have to readjust the size of the. Okay, so this is really what I have in mind. Now, of course, problems of this type appear in many other contexts, often in operational research, so logistic problems like inventory management. So this could also be a situation where these techniques could be used. I was thinking at more statistical side, what could be a case? Well, one situation could be a maximal marginal maximum likelihood estimator. If you that could fit in this setting, not so entirely sure that what I'm proposing, it could be meaningful in that case. Since last week was a workshop, many presentations on Bayesian experimental design. I was thinking whether this could apply also to Bayesian experimental design. Of course, there is an issue of nested expectation, which is definitely I'm not addressing in this talk, but could be some possible extensions. So as I said, I will focus on the strongly convex case. So I assume that G is continuously differentiable in U, in the design variable, for any outcome of the random variable. Gradient is L Lipschitz continuous, so with some constant that may depend on Y, but this Lipschitz constant is square integrable with respect to the underlying measure. And the functional J is alpha strongly convex, so we have a lower bound on the Hessian on this average G. And then in this setting, there exists a unique optimum, so a unique minimizer of this functional J, which is also the unique stationary point. So then we are after the stationary point of this function J. Okay, so that's the nicest setting, so we can do a gradient descent. So we just iterate in the negative gradient direction. If we do it with a fixed step size, well-chosen step size, so not too big, then the gradient descent, the full gradient descent will converge geometrically fast. So we'll have some parameters smaller than 1, and every iteration the error is reduced by the factor gamma. So super nice, very nice complexity, except that the full gradient descent requires the computation of this expectation, which is impractical. So then we have to approximate the expectation somehow. And depending on how we do this, okay, we might have a very high cost per iteration in computing this expectation here. So, of course, the alternative could be a stochastic gradient. Stochastic gradient, we just take a very poor, very cheap, unbiased estimation of the gradient. Easiest one is just we evaluate the function G, the gradient of G in one single realization of Y, or we could do a mini batch approach, but still with a relatively small n. And we draw this random variable yn independently at every iteration, independently from the past. So this estimator is unbiased conditional on the previous conditional on UK. That's an unbiased estimator of the expected gradient, of course, with a big variance. So the variance is O of 1, it's not small, but then the variance reduces over the iterations. So and then what is achieved in stochastic gradient in this case is a convergence on the mean square error. So I'm looking actually at the error on the optimal design, or could have looked at also the minimizer as a minimum of the function. Conclusions are about the same. So the mean square error on the optimal design scales like 1 over k, where k is the number of iterations. So it's stochastic gradient has a very low cost per iteration, so just one gradient evaluation or a few gradient evaluations, but the convergence is rather slow. It's 1 over k on the mean square error compared with a geometric convergence that theoretically full gradient could achieve. In this case, yes. No, not always. Here I'm assuming that I can. So things are nice and differentiable. Then, of course, there are works that have looked into this and said, can we improve the convergence of the stochastic gradient and somehow recover a convergence of the full gradient, still having a relatively low cost per iteration. And so there are several ideas of variance reduction in stochastic gradient. And there is a saga, the saga, which I'm mentioning here, the SVGD, and then follow-up works. So here I'm recalling the saga one that was proposed in this paper by 2014, so about 10 years ago. And it works when this random variable y is actually a discrete random variable. So the measure is an atomic measure. So this expectation is actually a sum. It could be a sum over many terms, but it still can be written as a sum over S terms. So the typical situation is an empirical loss that you want to minimize in machine learning. And the idea of saga is to essentially keep track of all the gradients that are evaluated during the evolution of the stochastic gradient. and using all this information to provide a variance reduction. So essentially the idea is to keep a memory term, and actually the memory term contains the best evaluation that you have of the gradient in each point yj. So you have, since the measure is discrete, so you have only s possible values of y, and then you store the best estimated that you have of this gradient in each point, in each of those points. So this memory has size s, or s times d, if d are the number of components of the gradient. And of course, you have to initialize. You could either initialize to 0 or initialize to a constant value. So you compute the gradient in one point, and then you assign this to all the other points. And then the algorithm is relatively simple. So at each iteration, you draw one index, 1 to s. So you pick randomly one of these points, and you evaluate the gradient in that point for the current design UK. And then you do an update using this estimator of the gradient, which is of control variate type. So you take this estimation of the gradient and you subtract the estimation that you have from the memory. So this acts as a control variate. And then, of course, you have to correct. So you have to sum the expected value of this random variable. So here the randomness is from the index j that is picked randomly. So the expected value of this is just the sum of all the average of all the terms in the memory. Okay, so this average is your best estimation from the past that you have of the expected gradient. And then you do this correction here. So, and of course, once you have done this update on the control, on a design, then you want to update the memory. And the update the memory is very simple. So in the position L that corresponds to the index that you have drawn, you replace whatever you had in the memory with a new estimate. And all the others remain unchanged. So every time you visit a point, you compute a gradient and you replace in the memory, you put the latest estimation in the memory. And you keep on doing this. Okay. Yes, exactly. So the memory is not consistent because you have estimations at different UKs, but every time you update with the latest one, and then since you hope that UK is converging to the optimum, this memory becomes more and more consistent and eventually becomes almost an exact approximation of the full gradient. Not necessarily. The psi KL is the gradient evaluated for in this point YL whenever you have visited that point. So it could be is not evaluated at UK. It's evaluated at past iteration when you have visited this point YL. Maybe you have never visited this point, so it's just the initial estimation. Exactly. It's a different U from the past, the last time that you have visited that point. So what was proved in this paper is that actually this, at least in the strongly convex case, this algorithm does recover the convergence of the full gradient. So is a geometric convergence, so let's say exponentially fast, still with just one gradient evaluation per iteration. Okay, you might say there is a cost in computing this estimation, but actually you can just store the average and update the average every time, so the cost is relatively limited. Of course, there is a big price, and the big price is the storage. So you have this memory to keep track, and if S is very large, you need a very big memory term. And the other issue somehow is what is this gamma here, and actually this gamma is of the order of 1 minus 1 over S. So actually, if S is very large, the convergence is geometric, but not so fast at the end. Okay, so there is somehow a degeneracy when the number of points becomes too large, both in terms of memory storage and in terms of convergence. So we did use it for this, in this previous work, for this stochastic optimization problems with continuous random variables. And the idea was, okay, let's suppose that the problem is nice, so G depends smoothly on Y, so I can pick a good quadrature, maybe let's say Y are Gaussian random variables. I take a tensorized Gauss-Hermite quadrature formula. It's very accurate, but potentially with many points. So I don't want at each iteration to go through all the quadrature points. So I use Saga in this framework. So I replace the expectation with a weighted average. Okay, now the weights are not necessarily all equal, so I will have to adjust the Saga to this case of non-equally weighted terms. But then I play with the Saga, so at each iteration I just pick up one quadrature point, I evaluate the gradient in that quadrature point, and I keep on iterating. Okay, and essentially we could extend, generalize the theory in this context, and everything works quite nicely, except that, of course, if this quadrature has very many points, you run into the issues that I mentioned earlier. So you have a big storage problem, and the convergence is slowed down. So somehow there is a trade-off on the accuracy of the quadrature that you want to use here and the speed of convergence that you want to achieve. So then the question was, okay, but can we avoid this quadrature step? Could we try to approximate directly this expectation somehow? So using some other type of control variates. So here is a general framework. I'm not claiming there is anything new here, but this is just more general setting or framework to set this problem. And they could work both with continuous and discrete random variables in principle. Again, our focus was more on the continuous case. So suppose you have a model. Now in Saga, this model is essentially this random variable here that has stored all this gradient information, but you could use some different model that I call VK, which is some model for the gradient of G as a function of Y. So now ideally this model should be a good approximation of the gradient of G evaluated in the current point. It will not be a perfect model, so it will use this G evaluated in some previous iterations, but it should aim at approximating this quantity here. And we build this model using previous iterates up to SK previous iterates, previous gradient evaluations. So we could use this history of SK gradient evaluation to fit a model. I will focus on regression model, but one could think of using also other models like kernel interpolant, maybe a GP. So you try to fit a GP over the history and then use this as a control variate. The assumption is that the expected value of this model should be easy and cheap to compute. So again, if you do regression, your dictionary should be simple and you should be able to compute the expected value cheaply. And this model uses a memory, which is again the history of all the past SK past estimates, so the gradient estimates, and I should also keep track of the evaluation points Yj. Now they are not fixed, they will be picked randomly, so I need to know where the gradient was evaluated. Okay, and then the algorithm would work in this way. So we have to initialize the model somehow and initialize the memory somehow. And then we can start iterating. At each iteration, we draw one realization of Y from the underlying measure rho, independently from the past. We evaluate this gradient at the current design UK in this point YK. And then we do our gradient descent update with the estimation of the gradient, and the estimation of the gradient looks similar to the saga. So we take the current evaluation of the gradient, we subtract our model evaluated in this draw yk, and then we have to correct it back to get an unbiased estimator, so to add the expected value of the model, of the current model vk. Once we have done this, then we updated the memory, meaning that we have to add this new gradient evaluation in the memory and maybe throw away the very last one if the size of the memory doesn't change. If the size of the memory changes, then we keep increasing the memory. And once we have updated the memory, we update the model. S is the memory, so it is the FK is a sigma algebra for all the past. So everything is conditioned on the past. So SK is the memory, so all the past gradient evaluations that we use to fit the model. Here I'm assuming that the memory could depend from one k to the could change over k, and the model also, the model structure could change from one iteration to the next. It's not necessary we could keep it fixed. We could keep fixed the dictionary and the memory size, but we could also increase the dictionary and the memory size over the iterations. Okay, so this estimator is still conditionally unbiased, so it does still fit in the general stochastic gradient philosophy, and the hope is that the variance get reduced more and more over the iterations, so maybe we can recover the exponential convergence. So just a couple of improvements. So it's not difficult to add to this an important sampling step. So maybe to build the model V, it's better not to sample from the original distribution rho, but from some other distribution that I call mu, so a sampling distribution. Maybe it makes this construction or regression more stable. So this is not difficult to achieve. So we sample from a different distribution mu, which should be, so rho should be absolutely continuous with respect to mu. And then we have to add the correcting factor here. So the density of rho versus mu evaluated in the current point to recover an unbiased estimator. Okay, so that's not, doesn't change much. We could go even farther and say, okay, if we change the model from one iteration to the next, maybe this sampling measure should also change from one iteration to the next. But that causes a problem, because it means that the new draw will be from the new sampling measure, but the past ones will be from the old sampling measure. So if you want to keep a consistency on this sampling measure, one could do some resampling of the past, of the history. So suppose that the new sampling measure is a mixture, so it's alpha times the previous sampling measure plus a correction, a delta, and eta k. Okay, so ideally I would like to have all the y's that are at iteration k plus 1, all the y's that are sampled from mu k plus 1, but this will not be the case because the history have used the different sampling measures. So what I could do is, okay, when I have to update the model, the memory and the model, so I can go through all the indices in the memory, draw a Bernoulli random variable of parameter alpha k. So if alpha k is equal to 1, I don't do anything. If alpha k is equal to 0, then I redraw a new sample y tilde j. Why I call it tk? Sorry, this should have been a tj. So, y tilde j from this correction term. And I replace whatever I had in the memory with a new estimator, with a new evaluation for this new random variable. So I have to recompute the gradient in that point for that new random variable. So in this way, I can keep the memory consistent. So I call this resampling of the memory. This R operator is the resampling of the memory if I want to correct the sampling measure. Okay, so this would be the algorithm. So we draw from at iteration k, we draw from UK, we apply the estimator, we updated the memory with a new gradient information, then we updated the sampling measure, and then we do this refresh or resampling of the past memory to keep consistency, and then we can build a new model that uses this new sampling measure. Of course, it adds an extra cost here, but the hope is that if alpha k is very close to 1, so if this sampling measure is not changing much from one iteration to the other, this extra cost is under control somehow. Okay, so that's a general idea. And of course, I think there are many directions that could be explored in this framework. So what we have looked at is building this model by regression. And I'm particularly fond of this let's say polynomial least square type models. But it doesn't need to be polynomial. It could be just a regression, some linear subspace. So the idea is to consider a sequence of approximating spaces, larger dimensions. So VM has a dimension m, so that this sequence is dense eventually in L2 row, so in square integrable random variables. And then at iteration k, we construct a model vk by doing a least square regression in this space vmk. So we can choose the size of the space. We can keep it fixed, or we can increase the size of the space over the iteration. Okay, here I use this notation is tensorized U, meaning that, okay, depends on what U is. If U is just R, you build R-valued function. If U is a vector, then you will have to do this regression for each component of the vector. If it is a function, you will have to generalize two functions. Okay, so then again, we have a memory that keeps the past iterates, and then we do a least squares problem. Again, maybe a weighted least square problem. The idea is to draw from a sampling distribution mu k, which is not necessarily a row. So when I do the least square, I add again this density d rho over d mu k, so that on expectation this is the mean square error with respect to the original measure row. Okay. And again, of course, again, this model is inconsistent because it uses all these evaluations of the gradient in different points UK. So it's not exactly a good model for a perfect model for the gradient in the current value, but the hope is that the more you advance in the iterations, the more all the past UKs look alike. So this model gets better and better, essentially. Okay, so that's a very quick, so I have worked in the past on this least squares problem, mostly with polynomial approximation. Let's say the best version is this one by Cohen and Migliorati in 2018. That's the optimally weighted least square, which essentially works the following. Suppose you have a smooth function that you want to approximate using this finite dimensional subspace Vm, and suppose that you have an orthonormal basis of this space, and you use a certain sampling distribution mu, not necessarily a row, and you draw IID points from this distribution mu. So this is just function approximation. It's not yet within the stochastic gradient. And then we want to do a weighted least square, so we compute this discrete least square projection, minimizing the distance between the V in the subspace and the psi, evaluated in these sampling points with this correcting factor here for important sampling. This is a quadratic problem, so easy to solve. It just boils down to solving a linear system. So if I expand this object on the basis, I will have to compute the coefficients in the expansion, which solve a linear system, where the matrix G is this Gramian matrix, where we have to evaluate all basis functions in all the points with this weight. And J is this discrete projection of the function over the basis. And this matrix G is actually the sum of or the average of IID matrices. So these basis functions are evaluated in every single point. So the points are IID. So all these matrices here are IID, meaning that this and in expectation they are the identity, because the basis is orthogonal. So in expectation, this gives the identity matrix. So this G is concentrating around the identity. So one can use some larger deviation results to say that eventually you don't need that many points S to have a stable reconstruction, because with high probability, this G is very close to the identity. It's not, it's with very high probability, it's not a certain statement, but one could always correct these projections. Okay, if I do, so I have this draw, IID. If it turns out that the matrix G is particularly ill-conditioned, I throw away my estimate and I just put 0. That's an easy fix. So if I correct the projector, this pi tilde is this least square projector whenever G is well conditioned. So if, let's say, the distance from G to the identity is 1/2 in spectral norm, and 0 if it is a bad matrix. So then with high probability you are in this case, and with high probability you have a good result, but not only with high probability, you have also in LP sense. So this is a fix that allows you to do LP estimates, essentially. So here is the result from that paper. It says that, okay, one should look at this quantity here. This quantity is the supremum of, you have to take your basis functions as a function of y squared times the weight and sum all of them. So this is a function of y, and then you take the supremum of this. And then you should take m and s. So m is the size of the subspace. S is the number of points that you use. So they should satisfy a sampling inequality that looks like this one. So k depends on m. Okay, this value here depends on how many terms you have in your subspace, whereas this depends on s. So the ideal case is where this constant is exactly equal to m. That will be in the next slide. So if this constant is exactly equal to m, this rule says that you should keep a number of points that is of the order of m log m. Okay, to have a stable reconstruction is enough to have a number of evaluation points that is of the order of the dimension of the subspace up to log terms. So if you do this, then you can show that the mean square error between the original function and this reconstruction here is up to constants that are nice and can be quite precisely quantified, is essentially the best approximation error that you can do in the subspace. So this is the best L2 approximation error in the subspace. So you lose very little by this discrete projection with respect to an ideal true projection, plus a term that comes from the fact that we have a certain small probability of doing garbage, essentially. So this small term can be made arbitrarily small. That's where this parameter R enter. Of course, you can make it arbitrarily small. If you take R big, this will impact this constant, so it will impact the sampling inequality. So if you really want to get this term very, very small, you will have to oversample a lot. But if you just aim at keeping this term of the same size of this one, maybe the oversampling is minor. Okay, I don't remember what is, yes, what is written here is that this was for a real valued function, but everything generalizes for vector valued functions or Hilbert valued functions, so it's not an issue here. I said the ideal situation is where this constant is exactly equal to m. Can we achieve it? Answer yes, because if you take a sampling measure that is exactly equal to essentially this density here, you get one. You get this result. So if your sampling measure is exactly equal to this average of the sum of the basis function square, if you just replace this in this result, you see that the constant is exactly equal to m. So there is a notion of optimal sampling measure, optimal in the sense that is the one that makes this projection the most stable. And this is a recipe. So in this case, the sampling inequality is exactly what I was saying before. The oversampling is just a log factor. So the number of points that you need is m log m, essentially. Rho is a target, and this is a definition of my, yeah. Okay. And actually, it's not difficult to see that if we increase the space, this sampling measure will change. So this sampling measure depends on the space, but we could build it in an incremental way. So if I have increased the space from VM to VP, I can write this sampling measure on VP as the sampling measure on VM with weight m over p, plus a correction, and the correction takes the basis functions that were not in VM. Okay. So again, if you increase slowly, the sampling measure is changing a little bit from one step to the next. So you can play this trick of doing the Bernoulli sample if you need to refresh the sampling. Okay, sometimes it's difficult to sample from this. So this is a mixture, by the way. So sampling, you just pick up one basis functions, and then you need to sample from this psi I square, maybe acceptance rejection, or maybe some MCMC. I mean, and the assumption here is that sampling from Y is not costly. What is costly is the gradient evaluation. So I can invest in this sampling without compromising the efficiency of all algorithms. One could also look at some quasi-optimal sampling measures. So sampling measure mu is quasi-optimal if essentially it compares, the density compares to the one, to the optimal one, and is known for certain cases. For instance, if you work with uniform random variables and Legendre polynomials, if you take the arc sign distribution, this is a quasi-optimal measure. So it achieved this bounds here. And if you use a quasi-optimal measure, the sampling inequality is worsened by this constant C2. Okay. If this is not too big, you can still use a quasi-optimal. Okay, so this would be the algorithm if we use this least square approximation. Yes. How do you choose M? So if you just want to do approximation of a function, well, ideally you have to choose M so that this best approximation error is small, which you don't know. So in practice, you can try to with some M and then increase and see how the error is decaying. No. Yeah, yes, it's another approach. So here I'm regularizing by projecting on a small subspace. The other option would be to add a penalization. The penalization, if you want to get the optimal rate, you have to know the function class. So you have to tune how the penalization is drawn to 0 when you increase the number of points. And the optimal choice depends on how smooth is the function. Here, you don't have this limitation. So the smoothness doesn't appear. It's just a quasi-optimality result. But then, yes, in practice, you have to decide how big is the M. Now, in the next slide, I go to the stochastic gradient. So in the convergence, the question that we asked is, how should we increase M over the iterations? And that's a crucial question because we cannot increase too fast. Well, there is an obvious limitation. It cannot be larger than the number of iterations because then we don't have enough information to fit the model. But could it increase linearly or sublinearly with respect to the iterations? That was a question, essentially. So I will answer the few slides next. So this is the overview of the algorithm. It's the same as before. I've just particularized for the case of the regression. So this is for a fixed subspace. If we fix a priori VM and the sampling measure mu and the size of the memory that satisfies this sampling inequality, Then we iterate. At each iteration, I draw one realization from U. I evaluate the gradient, and then I use this control variate, where I subtract this least square projection plus the mean, and then I update the memory. So in this, with the fixed subspace, the memory size doesn't change, so I just have to add the new one and throw away the oldest one, and then recompute this least square projection. Now you may say this least square projection is very costly if the memory is big, but actually you can do it efficiently, because if you solve it by factorizing the Vandermonde matrix by QR factorization, when you go from one step to another, you have added one data point and you throw away the oldest one. So it's a rank 2 correction to the Vandermonde matrix, so you can do efficiently an update of the QR factorization. So eventually it doesn't cost that much. Okay, so this is the first result in the case of a fixed subspace. So the fixed subspace, of course, has the drawback that you have to choose in advance the size of the space. Of course, so this was more first step toward the next result. But, so if you fix the subspace, this means that this control variate asymptotically will not converge to the full gradient, because it will always be a projection on a fixed subspace. So you will never achieve in the limit 0 variance. So it means that either if you really want to converge to the optimum, you have to reduce the learning rate over the iteration. If you keep it fixed, you will converge to something that is up to this projection error. You cannot do better than projection error. So here we kept it fixed, and then we could prove this result, this error recursion. So the error at step k+1 conditional on the past is a factor smaller than 1 times the error at previous iteration plus 2 error contributions, which come essentially, I mean, this is an error splitting. So we compared this gradient estimate, that uses this control variate, so this one here, with an ideal gradient estimate that assumes that you have evaluated all the gradients in the optimum. That's an ideal step. I mean, it's not computable, but I can split whatever error I have here in these two contributions, one that compares this with the ideal estimator with a consistent memory in the optimum, and the other that compares this estimator with the true value. So the B term is essentially the projection error on the subspace, because this is related to this least squares, and I compare with the exact value. So the B term will be of the same order of the discrete least square projection error. Whereas the A term is a comparison of these two estimators in different, so this one is the one that uses the whole history, and this one is the ideal one where all the evaluations are consistent in the optimum. So I assume the Lipschitz continuity of the gradient. So this one essentially relates to all the errors uj minus u star for all the j's in the memory. So you get an error recursion that is a bit nasty, because now you get the ek plus 1, that is a fraction of ek, plus a term that involves all the past errors in the history, plus a term dm, which is the best approximation error of the gradient in the subspace. So okay, then you have to work out this recursion with S step or S plus 1 step, no, S step recursion. So it's a bit technical. So the final result that we obtained with a fixed learning rate, as I said, if you want to converge, you have to shrink the learning rate. But then asymptotically, you will get the convergence of the stochastic gradient, not better. Hopefully with a much lower constant, because you have a good control variate. But so if we fix the learning rate smaller than something, then the error will decay geometrically. So the initial error will be damped exponentially fast, but then you have a residual error that is due to the projection on the subspace. Okay. So in a sense, it's similar as if you were doing this approximation directly on the original problem, and then you run a full gradient with this approximate gradient. But the advantage here is that you do it on the way, you learn it on the way, so and you just have one gradient evaluation per iteration. Okay. So the more interesting case, but again, this is somehow similar to Saga. So this gamma scales like 1 over S, where S is the size of the memory. So the more interesting case is when you try to increase the model over the iterations. And then the question is what I was saying before. So what is the optimal scheduling? So how fast should I increase the size of the memory and the size of the model? I don't claim that this result is the best ever. So it's the first result that we could obtain. So okay, this is just the algorithm. So, and if we increase the size of the subspace and we want to do this quasi-optimal projection, then we need to change the sampling measure over the iteration. So we have to go through this resampling of the measure to keep the consistency with the pass points and so on. So we have analyzed this full algorithm here. And let me discuss first this case, which is nicer. So the first case is where this projection error, this L2 error for when this is the exact L2 projection error. We know that the discrete, when we do this discrete squares, if we satisfy the sampling inequality, the error is up to constant equivalent to this best approximation error. If the best approximation error decays algebraically in m, like m to the minus eta, and this, okay, depends on how smooth is your G and what is the dimension, but you can get the results of this type. Then the strategy here is essentially to do like stochastic gradients. So you shrink the learning rate like 1 over k, and we increase the memory size like k. So every iteration we increase little by little the they increase the memory, and then there is always this log factor, so the mk will be sk over log k, so it's slightly less than k. So if we do this, we could show that we recover essentially this algebraic convergence rate. So the error at time k, the mean square error at time k, is of the order of k to the minus 2 eta. There are some technical things here. There is xi that is involved, that is the maximum of this density, which may go to infinity, but it doesn't go usually too fast for certain nice distributions. So that was for the algebraic case. Yes. I knew this question. I was trying to go fast because I have to check the -1 because I'm not convinced either. Yes. Okay. Yeah. Yeah, I shouldn't be there. The -1, I agree. So we lose this xi because this density might blow up at a certain rate. So this doesn't blow up for uniform random variables, it blow up like square root of m for Gaussian random variables, so it's a mild blow up that reduces slightly. Okay, on the exponential case, we have a sub-exponential convergence. So if the error decays exponentially, then we have this other recipe. So the memory size should increase slowly at k to the 2/3. We got this magic exponent 2/3 just by balancing different error terms. And likewise, the learning rate should decrease like 1 over k to the 2/3. And with this, we get a sub-exponential rate, so we don't recover the full exponential convergence. But I mean, this is within the optimization, so we get mean square error that is exponential to the minus k to the 1/3 up to some constants. This still has to be improved, this result, because there is a strange dependency of the constant on this S. That is a parameter that you can choose. It means that the constant depends on S. You can take it too big. Okay, so this is what we got. Essentially, this is what I wanted to show. And again, the whole point here is just to do one gradient evaluation every time, and then you update this model over the iteration, and you can recover a convergence that is faster and potentially much faster than the stochastic gradient by learning these models through the history of the iterations. Okay, just a couple of quick results. So we applied to a couple of very toy problems. So maybe I'm running out of time. So a couple of toy problems. The first is just very simple. So it's a two-dimensional PDE with just one random variable because we wanted to check exactly all the things in the convergence. Sorry, it's here. So the PDE is the diffusion equation minus divergence of y grad z equal u. U is the forcing term, so in this case it's a full function in L2, but it doesn't change much. This random variable is an exponential of a uniform random variable, so we approximate in polynomial space using a Legendre basis in this case. We took a tracking type, so we minimize the expected value of this functional, meaning that we try to make the solution to be as close as possible to a target state on average, with some penalization of the control here. So again, the example is super simple. We took z target as an eigenfunction of the minus Laplacian, and then we have a closed form solution for the optimum, so we could check with the optimal value. And as I said, we do polynomial approximation with Vm being just the polynomials of degree up to n-1, expanded on a Legendre basis. So here is what the result with fixed subspace. So what you see, if I fix, for instance, a polynomial of degree 6, at some point the error will saturate because of this projection error. We are not reducing the learning rate here, but it decays exponentially fast at the beginning, so it looks like a full gradient at the beginning until you hit the plateau. If you increase the polynomial degree, the plateau goes down a lot, and the slope here is slightly reduced because you're working on a bigger subspace, so somehow you're a little less efficient. Here we tuned the learning rate for each case, so that's somehow the best curve that we could obtain. But this, of course, calls for an increasing m, so the idea now is to get somehow this envelope of these curves if we increase the size of the space. So this is what we did here. The green curve is essentially the method that we are proposing, where we do this increase of the dimension of the space over the iteration, learning this projection from past iterations. The red one is one where we fix the step size. It seems to work also quite well without shrinking the step size. So the balancing the error term gave this recipe of how to shrink the step size, but it seems that also fixed step size works, because in this case the variance is going to zero asymptotically. The yellow one, no, orange one is the saga. So here we use the 20-point quadrature formula, Gauss quadrature formula, fixed beforehand. And then we ran the saga with this discretized expectation. And this is the convergence, so it's also exponential. But of course, here you have the problem, if you take too few points, it will be faster, but it will saturate because you have a quadrature error. If you take a big quadrature, it will probably go up to machine precision, but then you slow down because you have many points to revisit at every side iteration. So somehow this adaptive learning is more interesting because you just increase on the way the approximation space. This is a slightly more challenging case, but still very simple. So it's a diffusion transport diffusion equation. So we added transport term and the right-hand side f of y, and there are 5 random variables in this on the diffusion, on the vector field here, and on the forcing term. So the forcing term is a Gaussian bump placed on a random position y1, y2. So again, still 5 random variables to be able to compute a reference solution and see how things compare and converge to the optimum. Again, the same type of functions. We try to minimize the norm of z by acting with a control here on the right-hand side. So we want to put a sink somewhere to minimize the norm of the size of the contaminant. And in dimension 5, we still work with polynomial spaces, but with this type of hyperbolic cross spaces, meaning that we take all monomials in the 5 random variables, and we look at the degrees, and the product of the degrees should be smaller or equal than m. I mean, the standard polynomial space would be the sum of the degrees, but here we take the product of the degrees, which has a much coarser, sparser shape, so much fewer terms. So it's a good space if you have some nice regularity, so-called mixed regularity. And the size of the space grows like, so m is the maximal degree, and the size of the space grows almost linear, so m log m to the power 5. So again, those are the results on the fixed case and increasing case. So in the fixed case, I mean, the situation is similar as before. It's much more noisy in this case. So if we work with a small space, so 11 terms, we have a fast convergence at the beginning, but then we saturate. If we take a much bigger space, we slow down the convergence, but it's saturated at a much smaller error. And if we do adaptive, so if we progressively increase the space, we get a convergence that looks quite nice here. And again, it compares, it's much better than doing it a priori discretization of the quadrature and running Saga on the discrete, on the approximate expectation. All right, that's pretty much it. All I will say, didn't put a conclusion slide, but the conclusion is that I think that's an interesting approach. There are probably many directions that could be explored, either on, I mean, here we look at this regression on polynomial spaces, but as I said, one could think of many other type of models that you want to build over the iterations. We look at a strongly convex case. Of course, that's the nicest case to the theory. So how these things work in the non-convex case, big question mark at the moment. Open to suggestions and questions.
Naturally, with non-parametric, you will go with your data. So, what is your comment? I mean, textually.
If you do smoothing, and it would be very similar as long as you can show good results for this approximation. So as long as you have a good sampling measure that places the points in the right way, and so on. One could also think of doing adaptive sampling. I don't know, you try to build a GP, and then you try to place the new point in a good way. And then the theory would be much more difficult, I guess, to understand this adaptive. Yeah, I think they should extend to these other cases. No, we have not tried, so yeah, I can't answer.